Okay, so we've talked about center of mass. Then we talked about rotational kinetic energy, 1/2 I omega squared. And of course, that brought up that whole discussion about the I, the rotational inertia, right, in this thing. Now we're going to talk about the rotational equivalent of force. And that's called torque. Torque. So here, oops. Okay, a force causes a linear, so what? Acceleration, right? F equals ma. A torque causes an angular gas acceleration. So that's what I mean. Torque is the rotational equivalent of force. But as, again, look at, you're going to be careful, right? Torque causes angular acceleration because, it's rotational. Okay, so torque, rotational equivalent of force. I just said that. All right, so this is a torque wrench. And so these wrenches, they measure the torque. So why would you want to do that? So this is my bicycle, and this is the screw that holds the seat on the seat post. And it says right there, well, hold on, can't see it. It says maximum torque, 8 Newton meters. So if you exceed that, you might break something because this is carbon. And so obviously you want to have a torque wrench so you don't tighten it too much and break things. Okay, now here's a kind of a nice question for you. A disk is rotating about an axis. In order to maintain a constant angular velocity, a constant torque must be applied to the disk. Ignore friction. So is that true or false? In order to maintain a constant angular velocity, a constant torque must be applied to the disk. True or false? So pause your video and figure it out. Okay, just think about it. If you're out in deep outer space and you throw something, what's going to happen? It's going to go at constant velocity. Now, are there any forces acting on it? No. Well, how about this? Are you going to need a constant torque to maintain constant velocity? No. If you have a torque, remember, torque is like force. If you have a constant torque, you're going to have a changing angular velocity. So it's totally false. Totally false. Okay, now let's walk to the door. So I'm going to show you something about this door. All right, so here's a door, and this is the axis of rotation. Now, if I want to open the door, the appropriate thing to talk about is torque, right? Because it's rotational force. Now, if I want to open this door, where am I going to push it? Well, everybody knows that. You open the door, you push it here, right? It's nice and easy if you push it here. Well, how about if I push it here? Okay, if I push it here, forget it, right? I mean, it's really difficult. It's like impossible, you know what I mean? All right, now let's say I get over here again. All right, now, if I want to open it, I'm just going to have my finger perpendicular to the door, right? Well, how about if I had it at some crazy angle? Like instead of having it perpendicular, how about if I push like this, like this direction? It's going to be really, really hard to open a door, right? Okay, so when you're talking about torque, there's more to it than just force, right? What's also important is where you apply the force, right? If it's close to the rotation axis, forget it. It's going to be very difficult to open the door. If it's far from the rotation axis, yeah. But it's more than that, too. It also depends on the direction, right? Like this is going to be easy, that's going to be hard. So torque, way more complicated than force. Okay, so this is the kind of what we just talked about. This is the top view of the door. So this is the hinge, which I'm going to call the axis of rotation, because that's what it is, right? Okay. And let's discuss these. Okay. So where would you, being a normal logical person, where are you going to press? or push to open the door. You're going to do this, correct? I mean, if you do this, it's going to be really challenging. If you do this, it's going to be challenging. If you do this, total waste of time. It's not going to open the door, right? Okay, so obviously we have to get an equation, right? We've got to get an equation for torque, and we're going to have a couple of them, you know. But all I'm saying is, again, so torque depends on the magnitude of force, the direction of the force, and the location of the force. So 3 things. Okay, so again, we're going to have at least 3 equations for torque. So, but it's all right. All right, but first let's just talk about magnitude. We'll just keep it simple. Magnitude of torque. Woohoo! Okay, all right, magnitude of torque. So the this is a Greek tau. That's what we use for torque, Greek tau. So torque equals the force times d. What's d? This is what gives you trouble for most people. It's called the lever arm. And you have to know how to calculate that lever arm. What the lever arm is, it's the perpendicular distance from the axis of rotation to the force line. What? Hold on, I'll show you. All right? Okay, so here, let's talk about this lever arm. All right, so torque is force times, yeah, by the way, some people call it a moment arm, some people call it a lever arm, whatever you like, okay? So let's talk about F1. What is this moment arm for F1? So here's how you do it. So F1 is this, right? So you just extend it to how far ever you need it, right? So this, I call this the force line. Okay, just extend it to however you need it. So that's the force line. And in the lever arm, it's the perpendicular distance from the axis of rotation to the force line. So it's this, right? Okay, right? Perpendicular distance from the axis of rotation to the force line. So you can see that F1 has a really, really long lever arm or moment arm. And that's why it's easy to open a door there, right? Long lever arm. Okay, let's keep going. Okay, what is the lever arm for F2? So think about it. What is the lever arm for F2? Well, this is the force line, right? You just extend it, you know, you just extend it however that's okay. So what's the perpendicular distance from the axis of rotation to the lever arm? 0, right? So no, there's no moment arm. That's why if you apply a force F2 as shown, you're wasting your time. You're not going to open the door. Okay, how about F3? I wish we were in class because I would have a student come up and show everybody where the lever arm is for F3. So pause your video and you figure it out. Okay, so again, what's the step? You extend the force, you make the force line however long you need it, right? So just pretend there's this force line. And then the lever arm is the perpendicular distance from the axis of rotation to the force line. So for F3, that's the force line, right? You just extend it. And then the lever arm is perpendicular distance. So there it is. Okay? And, you know, medium length, so it's going to be kind of difficult, right, to open the door if you push on F3 at that crazy angle. All right, how about F4? So you pause your video and do F4. Okay, so here's the force line. Then you want the perpendicular distance from the force line to the axis, right there. So that's really short, right? Really short moment arm. So it's going to be challenging to open that door because it's a short moment arm. So that's kind of like the summary, right? F1 has this nice long moment arm, so it's easy to open the door. F2, no lever arm at all, waste of time. F3, kind of a short lever arm. And F4, really, really short lever arm, okay? So there you go. So most normal people would apply the force along F1 because it's the easiest way to open the door. Okay, so that's equation number 1. Torque is the force times the lever arm. And again, I mean, I already said this, and you see it here, that the people, I mean, the challenging part here is to make sure you calculate the lever arm correctly. Okay, so that's one equation. Let's do another one. Okay, so here we have this blob. And this is the rotation axis. And we have, this is the position vector. Remember that from chapter, I don't know, way back, right? So this is the position vector, and then we have a force. So obviously, you know, the force is going to rotate it, right? Well, we want to get a different equation for the torque. All right? So let's just do what we always do. So let's extend the force to get our force line. There, that's the force line. And then the lever arm is the perpendicular distance from the force line to the axis of rotation, right? So there's a right angle right here, okay? So the torque is the force, F, times this lever arm, D. By the way, I just thought of something. Look at the units. So torque is force times lever arm. Force is newtons. Lever arm is meters, right? So torque, Newton meters. So when I showed you a picture of my bicycle, remember it said maximum torque. I don't remember what it was, like 8 Newton meters. All right, but anyway, that's just for remembering that. All right, so let's keep going. Oops, sorry, you didn't see that? Okay, so what is an equation for this D? In other words, so this is angle phi, this is angle phi, here's R, right? So what's an equation for D? I want to get rid of my D. So what's D in terms of R and the angle? Well, it's sort of obvious, right? D, it's opposite, right? So it's the sine, R sine. Okay, so we substitute for D, we get R sine phi. All right, now if we felt like it, we could change the parentheses around. Who cares, right? We could write like this, F sine phi times R. That's not a big deal. Now, F. We could decompose F. We always do that, right? Let's say that this is the nice, let's say this, we want to see what F is along this axis and what's perpendicular to that. Let's decompose F. Okay. So now this is parallel to this, and this is perpendicular to it. So put a little R here for rate, put a little T there for tangent. Okay. Now, what is this? What's F sine phi? Look up there. What's F sine phi? Well, it's this, right? Which is this. It's Ft. It's Ft. So let's substitute Ft. All right. Now, does this make sense or what? I mean, what's going to rotate this thing? Is this going to be able to rotate this? No. How could it, right? There's no moment arm, What's going to rotate it is this guy. So that's just another nice equation for the torque. Okay, we use the other one more than this, but sometimes we use this, so you just got to whatever. All right, but that's nice because it just points out that the tangential force rotates the thing, not the radial force. Okay, so there you go. 2 equations. We still have one more to go, by the way, because you notice that these are just magnitudes. I mean, torque, right, it's the rotational version of force. So it has magnitude and direction. It's a vector. But all we're dealing with now is magnitude. You'll see why. So torque, force times D. D is the lever arm, the moment arm. Torque is FTR. R is the magnitude of the position vector, the length of the position vector. And FT is the tangential component of this F. So there you go. Use which one you like. Okay. Yeah, magnitude only. You see why I'm laughing. All right, here's a good question. You're trying to open a door that's stuck by pulling. Okay, you're trying to open a door that is stuck by pulling on the doorknob in a direction perpendicular to the door. Yeah, that's sort of normal, right? If you instead tie a rope to the doorknob and then pull with the same force, is the torque you exerted increased? So pause your video and figure it out. Okay, so torque is force times lever arm. Did you change anything? Not at all. So what's the answer? No. Okay? You did not change anything because you're still pulling this way, right? So you didn't change anything. All right, this is a really good one. You are using a wrench and trying to loosen a rusty nut. Which of the arrangements shown is most effective in loosening the nut? List in order of descending efficiency the following arrangements. So you want the best first and the worst last. So pause your video and figure it out. Okay, so remember, torque is force times lever arm. And now the forces are all the same. So this question is really about lever arm. Okay, so which one has the longest lever arm? Well, remember, so look at this one. So that's the force line. So this is the lever arm. So that, right? Because it's perpendicular distance. Lever arm perpendicular distance from the force line to the axis. So number 2 is obviously the best, right? That's going to be the most effective. So number 2 is the best. Now what? Well, let's see. Force line, lever arm. Force line, lever arm. The forces are the same. Lever arms are the same. So this is the same as that. Does this rod help? No, waste of time. Okay, total waste of time. It's like that question with the rope pulling on the door, you know? Okay, so these are the same, right? These are the same. But obviously they're not as good as this one, right? Okay, so 2 wins, and then 1 equals 4. So this guy's last, right? Why is it last? Because here's the force line. So this would be the lever arm. And this lever arm is certainly shorter than this one, right? So this is the worst. That's the worst. So there it is. Right? So 2 wins, 1 is the same thing as 4, and then 3 is the worst. Make sure you know that. Oh yeah, one more. Which Allen wrench will provide the greatest torque if the applied forces are equal? It's supposed to be silver. So the black one or the silver one. So, and you know the Allen wrenches goes like this, right? You know, you rotate them, right? So which Allen wrench is going to give you the greatest torque? The large one or the small one? The large one. Why? Because there's a lever arm, you know, because you're going to apply the force this way or something like that, right? And so let's say that this is the force line, and so the perpendicular distance from the force line to the axis is this. So this has a nice long lever arm. This has a short lever arm. This is going to be much more effective than this one. Okay, that's important. Oop. So weightlifting. Why do most people struggle with doing curls? I mean, why? You know, you do a press, you can do 100 pounds, 200 pounds, whatever, you know, easy. But with curls, oh my gosh, it's very, very difficult. Why is it so difficult to do a curl with a lot of weight? Well, guess what? I mean, isn't this torque? Aren't you rotating the dumbbells? Yeah, so it's torque. So why is it so hard to get a good torque doing curls? Well, here. So here's the question, right? What is the lever arm about the elbow? Because, you know, the elbow is the axis of rotation. Agree? Okay, so just use that first equation. Torque equals force times lever arm. What's the lever arm? Well, here's the force line. What's the perpendicular distance between this and the elbow? Right there. Not very large, right? Okay, so the lever arm is really, really small. And that's why most normal people can't curl very much weight because the lever arm is so incredibly small. Okay, here's a true story. So we used to have a long time ago, we had this Camry. It was used, nice red Camry. And so one day I came outside and I noticed the tire was flat. So big deal, change the tire, right? And we lived in Illinois at the time. And so I had one of these things. And, I tried really hard to remove the bolt. And I just really, really tried hard, but I don't know, I guess it was rusted on or something like that. So I couldn't get it off to save my life. So then I thought, oh, great, I got to get this tire fixed. And I got to change, I got to put the spare on. What am I going to do? And I thought, and I said, torque, right? Torque depends on lever arm. How can I increase the lever arm? Well, simple. I had a pipe, a metal pipe in the garage, a long metal pipe in the garage. So I just put the metal pipe over this, which made the lever arm go from like that long to like this long, and then just and came right off. What do you know? All right? So ever since, so with this particular car, I just put the pipe in the trunk, and I always had that pipe with us just in case, something like that happened again. Okay, so see, you just learned something useful. What do you know, right? Okay, now, I emphasize that in this equation, we're magnitude only. And we talked about magnitude only because it's important that you understand that, because it's not so bad. The direction is challenging, but not bad. Well, it is bad. All right, so now what we want to do is we want to do the direction. And again, this is a vector. This is a vector. But torque is a vector too, So you remember when we did work? So work was integral F dot ds. So we multiplied two vectors and we get a scalar. Well, now what we want to do, we want to multiply two vectors and get another vector. So it's a completely different operation. So we got to learn a new way of multiplying vectors. All right? New way of multiplying vectors. So here's the formula, and we're going to explain it. So this is the symbol for what's called a vector cross product. So it's a vector product because you notice that the result is a vector, and this is the symbol, so it's called cross, right? With work, we had a dot product, which was a scalar. Here we have a vector cross product. Oh boy. All right. So here, okay. So there's three ways of multiplying a vector. First way is the easy way, right? A plus A plus A is 3A. Very good. The second way is what we did when we did work. So A dot B is AB cos theta, and it's a scalar. What we're learning is this. A cross B equals C, right? So it's a cross, vector, cross. So this is what we want to talk about. Vector cross product. Okay, ready? All right. So here you have your vector A in terms of components, vector B in terms of components. The magnitude of this is just the magnitude of A times magnitude of B times sine theta. So we just write this as AB sine theta, right? Where theta is the shortest angle between the A and the B. I mean, it's not this angle, right? It's this angle, Okay, so all right. So cross product, AB sine theta. AB sine theta. Now, what was dot product? It was AB cos theta. Don't get them confused. AB sine theta. Okay, now that's the magnitude. But come on, we want the direction. So the direction is given by what's called the right-hand rule. The right-hand rule. What are you talking about? Okay, so here. So A cross B is AB sine theta times this unit vector u. So AB sine theta times unit vector u, where u is a unit vector found by using the right-hand rule. So what's the right-hand rule? So here it is. Okay, so here are two vectors, C and D, and they're in the same plane. So let's say we have a horizontal plane, and C is this way, and D is that way. So you notice that the cross product is perpendicular to the plane. Perpendicular. Now what's the right-hand rule? Well, here's how you do it. Again, horizontal plane, C is that way, D is that way. What you do, you stick your arm in the direction of the first vector, then you point your palm in the direction of the second vector, and your thumb, which is considered perpendicular to your arm, points in the direction of the cross product. Okay? So C cross D, all right? So again, horizontal plane, C cross D, so this is perpendicular to the horizontal plane, all right? So the cross product, C cross D, is perpendicular to the plane, which includes the the vector C and D. Kind of weird, but it's all right? That's what it is, okay? So this is always perpendicular to this plane. And that's incredibly important, especially in Physics 220. You'll see how important that is when you learn about magnetism and things like that. So here's another one, all right? So torque, right? So the R vector is this way, F vector is this way. This is the horizontal plane, and the torque is perpendicular to the plane. Okay, the torque vector is perpendicular to the plane of R and F, pointing in the Z direction. So I mean, think about it. If you have any two vectors, I don't care what two, if you have two vectors, they're always going to form a plane, right? Any two vectors will always form a plane. And the cross product is always perpendicular to that plane. Now, why is it the right-hand rule? Well, because like this, R cross F this way. If it were left-hand rule, it'd be down, right? And so that's why it has to be the right-hand rule, so you get it the up, not the down, all right? So right-hand rule. Yeah. Okay. You have to know how to do this. If you don't, you're going to have all sorts of trouble. So no joking. Stand up, and let's practice this right-hand rule. If you're going to take Physics 220, oh my gosh, we use this so often. But so we're going to use this now for torque. We're going to also use it for something called angular momentum. So you just have to know how to do this, okay? All right, so let's practice. So let's say I have R going that way and F going that way. So please stand up and do the R cross F. Well, I'll do it. Let's do it together. Okay, so again, we're going to see that the order is important. So when they write R cross F, they mean it, right? They don't mean F cross R, and we'll get to that. Okay, so the first thing you do, oh, by the way, there are two ways of doing this. I'm showing you the way I learned. There's another way of doing it with your finger or something weird like that, but I don't know how to do it that way. But anyway, so first thing you do, you stick your right arm in the direction of R, right? Okay? Then your palm faces F. So some people just do this, some people go like that, and whatever floats your boat, So R that way, I don't care how you have it. Then F is like that, so palm facing F. And then your thumb points in the direction of the torque. So the torque would be perpendicular to the whiteboard. Okay, let's do another one. Okay, what does that mean? So, a vector, you think of it like an arrow, right? And so if you draw something like that, that's an R, you're seeing the point of the arrow, the arrowhead, right? So that means that this R vector is coming out at you, okay? This would be the vector is going away from you, because this is like the feathers of the arrow. Okay, let's say R is like that, and let's say F is like that, okay? So figure out, let's do it together. and then you'll do some by yourself. Okay, so R cross F. So R, right arm away from you. Well, I mean, sorry, towards you, right? You're over there, I'm over here. So this is towards you, out of the board, right? Out of the board. So R is like this, F, palm that way, like that. The torque would be this way, okay, this way. And again, it makes sense, because what's the plane formed by this and this? Well, it's a horizontal plane, right? And so the torque is perpendicular, right? R cross F, perpendicular. Okay, let's do this one. You do it. Okay, so you figure that out. So pause your video and figure it out. Okay, let's do it. So R is into the board. So I don't know if you can see this, but whatever. R is into the board. F is that way, so it's down, right? So it's down. Okay, let's do another one. Let's do this. Okay, so you do it, please. All right, let's see if you did it right. So R is this way. F is this way, so it's that way. All right? Okay? Because again, you know, this is coming out this way, this is going out that way, so there's the plane. It has to be perpendicular to the plane. Okay, trust me, you have to know how to do this. If you have any questions, just ask, send me an email, or talk to the tutor, or just practice. Get a book or something, but you have to know how to do this vector cross product. I'll have a little bit more practice. Okay, let's do this. So, you know, these are the unit vectors, right? I, J, and K. Right? So I, J, K, right? Remember that? Right-handed coordinate system. I, J, K. All right? So, stand up. Okay, so I is coming out. J is this way. K is that way. So please figure this out. What is I cross J? So figure that out. Okay, so I cross J is K. Okay. Now do this one, J cross K. So do it on your own. Okay, so J is this way, K is up, so that way. So it's I, right? I. Okay, last but not least. Okay, now please on your own do K cross I. Okay, so K is this way. I is that way, so it's J. Okay, all right, I'm not exaggerating. You have to be able to do this. You have to. So make sure you can do it, or let me know or something like that. Let's quit.